There is a ghost in the machine of our reality, a particle that breaks the one rule that shouldn't be broken. You clicked on this video because you saw the title, you saw Richard Feynman, and you saw the words time reversed. And you might be thinking, okay, this is just another sci-fi metaphor, or maybe this is just philosophical poetry. I need you to understand something right now before we go any further. This is not a metaphor, this isn't science fiction, and this isn't clickbait. According to the equations that run your smartphone, the lights in your room, and the atoms in your body, antimatter is simply matter that is moving backwards in time. Richard Feynman didn't just suggest this to sound cool. He proved that if you want to understand how the universe works, you have to accept that the future can affect the past. Today, we are going to look at the proof. We are going to look at the day physics broke time. To understand why Feynman turned time around, we first have to understand the disaster that happened before him. In the late 1920s, a physicist named Paul Dirac was looking at an equation that described the electron. He was trying to combine quantum mechanics with Einstein's relativity. It was a beautiful piece of math. But there was a problem, a massive, glaring problem that kept physicists up at night. The math was telling Dirac that for every electron that existed, there had to be a mirror version. If an electron had a negative charge, the math said there must be a particle with the exact same mass, but a positive charge. At the time, this was ridiculous. No one had ever seen such a thing. It was like saying, I have calculated that for every person on Earth, there is an invisible evil twin living on the ceiling. It sounded crazy, but the math wouldn't go away. Dirac famously said that his equation was smarter than he was, and he was right. A few years later, in 1932, a man named Carl Anderson looked into a cloud chamber, a device used to track particles, and he saw it. He saw a particle that looked like an electron, acted like an electron, but it curved the wrong way in a magnetic field. It was the positive electron, the positron. Antimatter was real. But here's where the nightmare started. Physicists realized that when matter meets antimatter, they don't just bump into each other. They annihilate. They disappear completely, turning into pure energy, 100% efficiency. So we had a new problem. If the universe is made of math, and the math says antimatter exists, how do we describe it without breaking physics? See, usually, when we calculate how particles move, we look at their energy. Energy is supposed to be positive. You have energy or you don't. But the equations for antimatter kept spitting out something impossible. Negative energy. What does negative energy even mean? Does it mean less than nothing? If you have a ball with negative energy and you push it, does it move backward? The standard view of physics was collapsing. They tried to patch it up with complex ideas like the Dirac sea, imagining the universe as an infinite ocean of invisible particles. It was messy. It was ugly. Physics needed a savior. It needed someone who didn't care about the rules of how things should look. It needed someone who only cared about what worked. Enter Richard Feynman. Feynman was different. He didn't like complex philosophical patches. He liked pictures. He liked simplicity. In the 1940s, while working on what would become quantum electrodynamics, or QED, Feynman looked at this negative energy problem, and he realized something profound. He looked at the math for an electron. Then he looked at the math for a positron. He realized that if you just flipped the sign of time in the equation, the negative energy disappeared. Let me break this down because this is the moment everything changed. Imagine you are watching a movie of a billiard ball rolling across a table. It moves from left to right. Now imagine you play that movie in reverse. The ball moves from right to left. In classical physics, that's just a rewind. But in quantum mechanics, Feynman argued that a particle moving forward in time with positive charge is mathematically identical to a particle moving backward in time with negative charge. This led to the famous Feynman diagrams. These little doodles won him the Nobel Prize. In these diagrams, time usually flows from the bottom of the page to the top. An electron is a straight line going up, but sometimes you see a line going down. To a normal person, that looks like a particle moving down. But to a physicist, a line pointing against the flow of time represents antimatter. Feynman was saying, Stop worrying about negative energy in Dirac seas. Just treat the positron as an electron that is traveling back to the past. Think of it like this. Imagine you are looking at a road through a narrow slit in a fence. You can only see a tiny slice of the road. You see a car pass by going north. Then a few minutes later, you see a car going south. You think they are two different cars. But what if you could see the whole road? What if you realized it was the same car? It drove north, did a U-turn, and drove south. Feynman proposed that creation and annihilation of particles are just the U-turns in time. When an electron and a positron meet and explode into light, from a God's eye view outside of time, nothing was destroyed. The particle just hit a wall in time and bounced back. It changed direction. It stopped going to the future and started going to the past. This was the proof. The math worked perfectly. If you treat antimatter as time-reversed matter, all the paradoxes vanish. The equations become elegant. The universe makes sense again, but it opened the door to a thought so crazy, even Feynman was hesitant to say it out loud at first. There is a legendary story about this. It involves Feynman and his mentor, John Wheeler. One day, Wheeler calls Feynman on the phone. He's excited. He says, "Richard, I know why all electrons have the same charge and the same mass. Now stop and think about that. Why are all electrons identical? Every apple is different. Every person is different. But every single electron in the universe, from the ones in your brain to the ones in a star a billion light years away, is exactly 100% identical. They are clones. Why? Wheeler said, because they are all the same electron. The theory goes like this. Imagine the universe is a massive tapestry of time and space. There is only one electron, just one. It starts at the Big Bang, travels to the end of time, then it turns around. It travels backward in time all the way to the Big Bang. Then it turns around again, forward, backward, billions and trillions of times. It zips back and forth through history so many times that at any specific moment, like right now, while you watch this video, that single electron crosses our slice of time trillions of times. When it crosses going forward, we see an electron. When it crosses going backward, we see a positron. Feynman loved this idea. It was wild, it was elegant, and it explained the cloning problem. Of course, Feynman, being the pragmatist, found a hole in it. He asked Wheeler, if this is true, there should be an equal number of electrons and positrons. But there aren't. There's way more matter than antimatter. Wheeler, never missing a beat, joked, maybe the positrons are hiding in the protons. While the one-electron universe remains a theory, a beautiful, unproven thought experiment, the core mechanism behind it is standard physics. The part about time reversal wasn't the joke. That part stuck. In the rigorous math of quantum field theory, which is the most precise theory humans have ever invented, the time reversal operation is crucial. You literally cannot do the math without it. We have to accept that on a fundamental level, the distinction between past and future is not as rigid as we feel it is. So if antimatter is traveling backward in time, why can't we send a message to the past? Why can't I build an antimatter machine and warn myself not to make that mistake 10 years ago? This is where the macro versus micro world collides. Feynman showed us that individual particles don't care about the arrow of time. An electron doesn't know what yesterday is. It just navigates space-time. But we are not individual particles. We are massive, chaotic collections of trillions of particles. While one electron might be able to zigzag back and forth, the statistical probability of all the atoms in your body spontaneously coordinating to reverse direction is basically zero. This is the concept of entropy. The messiness of the universe increases. But here is the haunting part, the part that scatters your reality. The fact that particles can and do travel backward means that the structure of time is already laid out. If a particle can go from the future to the past, the future must, in some sense, already exist. You can't travel from a place that isn't there. If an electron comes back from next Tuesday to visit you today, then next Tuesday is already real. This suggests the block universe theory, where the past, present, and future are all frozen blocks of ice, existing simultaneously. We are just flashlights shining our consciousness on one slice at a time, moving forward. But the antimatter is moving the other way. way. It is the countercurrent in the river of time. While we are all being swept downstream toward death and entropy, antimatter is swimming upstream, back toward the Big Bang. Richard Feynman once said, "Nature uses only the longest threads to weave her patterns so that each small piece of her fabric reveals the organization of the entire tapestry." He looked at a tiny speck of matter, a positron, and he saw the threads of time itself. He taught us that our common sense is useless in the quantum realm. Common sense says time only goes forward. Physics says not necessarily. So the next time you hear about antimatter, maybe in a sci-fi movie or a news report about CERN, don't just think of it as explosive fuel. Think of it as a rebel, a tiny piece of reality that refused to go with the flow, a traveler from the future passing you by, waving hello as it journeys back into the deep past. Feynman didn't just give us a proof. He gave us a new way to see the world, a world where the impossible is just a diagram away. If this video bent your mind, you haven't seen anything yet. Click the video on the right to see why Feynman believed empty space is actually heavier than the entire universe. I'll see you there.